speaker is Ajit Kara. He's the PhD candidate at the Integrated 3D System Group, Department of Electrical and Computer Engineering at Georgia Tech. And so, yeah, I think it's so in Professor Bucky's group. His research focuses on the investigating the die-to-die signal, thermal, and power delivery challenges in advanced heterogeneous integration architectures and their impact on emerging device-based 3D computer in memory system. So yeah, Anjit, please go ahead with the presentation. Thank you.
Thank you, Dr. Wei, for the introduction. Sorry, I'm just trying to share the right screen.
Yeah.
Please let me know.
Yeah, please go to the full, presentation mode. No, it's, yeah, okay.
Okay,
It's,
is that better?
Yeah, better, okay.
Okay, great. Okay. So good morning, good morning to all attendees, and thank you, Dr. Wei, again for the introduction. My name is Ankit, and I will be talking about in this talk. I'll be talking about thermal reliability considerations of resistive synaptic devices for 3D compute in memory system performance. So here's the outline. I'll go over a brief background and motivation for this study, and talk about the proposed methodology that we use for this compute and memory reliability evaluation, present a few results, talk about future work before concluding. So state-of-the-art image recognition model parameters have grown exponentially up to beyond hundreds of megabytes for on-chip storage. And this basically is a constraint for the conventional von Neumann logic memory integration architectures, where basically the interconnect bus is a limitation in terms of how much bandwidth, effective bandwidth is possible. And in a sense, this corresponds to for some of the workloads that such image recognition processes require. They rely on conventional memory hierarchy, which basically requires the weights to be transferred from like storage class memories all the way down to the compute elements for typical von Neumann based accelerator devices, and also requires intermediate data transfer from the compute elements due to low on-chip storage. So there is like excessive movement of data. So this basically corresponds to potentially higher latency and power consumption, and of course due to the larger growing on-chip memory requirements, a higher cost as well. While a new paradigm in the form of compute and memory operation has been proposed as a potential method to address some of these growing image recognition and language translation model operations, and the idea here is to reduce this component of data transfer or data movement from off-chip to on-chip storage, and of course the movement of intermediate parameters as well. And this is done by potentially using volatile or either volatile or non-volatile on-chip memory, and store the weights or the parameters required for the entire operation on chip itself, and also highly parallel multiply and accumulate operations. Now, some of the benefits of such a method are shown in this chart I borrowed by Dr. M.F. Chang. So where they show is that their potential demonstration of the compute and memory system ended up with like in the range of 1,000 to 100 to 1,000, sorry, 10 to 1,000x lower inference energy. Now, embedded non-volatile memories are widely being adopted to replace conventional conventional SRAMs and DRAM memories for various reasons. Devices such as resistive random access memories have a high bit density and lower leakage, and thus provide higher embedded memory and more energy efficiency compared to SRAMs. So in this talk, we'll be focusing on the use of RRAMs, or resistive random access memories, for such operations. Among the different ways for dense memory and logic integration, 3D integration can provide like higher compute density and energy efficiency through a reduced footprint and lower interconnect length compared to conventional, 2D or like MCM, like multi-chip module and 2.5D architectures. And here I summarize some of the existing heterogeneous integration architectures, the landscape in this domain. And what I want to focus on, of course, as Dr. Swaminathan's talk and even Srijit mentioned some of the benefits of using 2.5D and 3D integration techniques. There are certain challenges as far as thermal considerations are concerned. So as even Srijit talked about the issues of at increasing package powers, and of course, like increasing thermal coupling, which are definitely increasing or definitely challenging in 2.5D systems, but even more exacerbated when we go with 3D. So there are some benefits, but we'll talk about some of the challenges as it concerns with integrating these emerging non-volatile memory devices as well. So on the left, I show a power density trend over the last few years in like demonstrated computer memory and neural network hardware accelerator prototypes, where a clear increasing trend in power density is observed. Now, as far as resistive random access memories or RRAMs are concerned, one key challenge is lower retention due to higher temperatures, which can be more significant when we consider dense memory logic integration because of increased in 3D because of increased volumetric power. So there are definitely there are work in the there's work in literature which has looked into such challenges, but they've mostly considered device level effects, or they've been limited to 2D integration. But a requirement for early exploration of 3D integration of such devices and this equivalent impact on system level performance is imperative. So with that, I'll talk about our proposed method for this reliability evaluation. So we propose to estimate the variation of resistance across across the memory tier, the RRAM bit cell array, which is integrated in a 3D form factor. And we do this by proposing a device, system, and application level methodology. So we look at the impact of different integration architectures on the reliability of RRAMs for CIM. And we also benchmark heterogeneous accelerator designs, where we look at logic on 7 nanometer CMOS and memory at 22 nanometer RRAM integrated in 3D. So for this, we use an updated framework, a finite volume method-based thermal modeling framework for the system level evaluation, a measurement calibrated hafnium oxide-based RRAM device model for the device operation, and a neural network or compute in memory accelerator benchmark framework, which is DNN plus NeuroSim, which our collaborators developed. So for this study, we looked at the VGG8 network, and our target data set was CIFAR10. And from an integration perspective, we assumed a logic tier and a memory tier, as shown here. And we assume they are integrated in two methods. One is a through silicon VR TSV based and microbump based 3D, and the other is sequential stacking or monolithic 3D. So from an architectural perspective, the logic tier holds all the ADCs and some of the peripherals. and the memory array holds all the RAM arrays. So shown here on the left is the flattened layout for both tiers, the logic and memory, shown over here, and the representative power density maps and the floor plan for TSV-based integration and monolithic 3D integration. So key difference here is the total interconnect area for die-to-die integration, where we assume a larger TSV, like we assume a TSV diameter of 1 micron, and for fixed number of TSVs or fixed number of interconnects for memory logic in the first case, and the second case we assume a much smaller scaled diameter for interlayer vias for the 3D integration. And in terms of the interconnect pitch, we assume a scaled state-of-the-art microbump with 36 micron pitch, while a much lower landing pitch for ILVs in the monolithic 3D case. So now I'll talk about a couple of the benchmarking studies that we looked at using this proposed methodology. So the first thing that we looked at was a steady state thermal evaluation of this using this flow. And there were three key knobs that we have had in this study. One was the configuration, where we consider memory on logic and logic on memory. The second was integration type, which I already talked about. And the third was the cooling architecture assumption. And we assumed air cooling, conventional air cooling, and microfluidic cooling. So some of the assumptions of the boundary conditions I've skipped for brevity, but I have them in backup, and if interested, I can go with them. So what we noticed in the results was there are two key things. First was for air cooling. Looking at just the memory tier, here are the results, the contour plots for just the memory tier in all four cases. For both configurations, the junction temperature for TSV-based 3D was lower than the monolithic 3D, which is basically can be seen over here if you just look at the memory tier. And this basically, one of the key reasoning, I think we understand the reasoning is better isolation due to the presence of underfill layer between the two dies, while that it does not exist in monolithic 3D integration. So there's more a larger thermal coupling, steady state thermal coupling between the tiers. So what this basically means is the retention the device retention would depend on the integration and the cooling type. And for microfluidic cooling, we observed like significantly lower temperatures across all cases. Now, the second set of analysis was a device level evaluation. So the junction temperature as a function of power and boundary condition that we obtained for the memory tier is used as inputs to the device model to evaluate the change of bit cell resistance over time. So essentially the retention characteristics of the device. So what we observed was, there was a drop in retention, or the drop in retention was delayed. Basically, the increase in resistance for the device was delayed, starting from the initial time to up to almost like 10 to the power 7 second time frame. In all cases, in monolithic 3D air and also TSV-based 3D using air cooling. And one key reason for this was that we sized up, we scaled the heat spreader size such that junction temperatures were maintained below catastrophic limits. And the trade-off with this is that larger heat spreaders can have limitations in practical use cases from reliability and integration as well. And of course, with liquid cooling or monolithic microfluidic cooling, we observed like significantly lower change in device retention resistance. Now, the final evaluation was how the retention model that was obtained, updated retention model obtained in the previous step, can impact an application. And for this case, we consider representative image inference as a representative application, and we evaluate the inference accuracy over time for the different integration and configuration types that we have considered. Now, what we observed was shown here is the inference accuracy over time for the three key cases that we're looking at, and I show a zoomed in view of the key like the key area of interest, where we noticed that at close to almost 10 years, which is the standard retention time period defined for most memory devices, the monolithic 3D noticed a much larger drop in retention or drop in inference accuracy compared to TSV based 3D. Of course, I went over the reasonings for these, including like a higher impact from the high power logic tier on the memory tier in monolithic 3D. But of course, there are methods of mitigation. And one method that we evaluate is the efficient cooling architecture, which noticed significantly lower change. While also there are other methods such as potentially reliability aware IP partitioning, which could help reduce the thermal impact. As far as future work is concerned, we want to look at potential ways to validate our results with hardware, and for that our group is collaborating with Dr. Shimengyu's group at Georgia Tech, where we look at their fabricated like compute in memory modules or chips, and we try to emulate a 3D stack behavior by fabricating active heaters on the back side of the chip, like both on the back and the front side of the chip. So this work is ongoing, and we hope to gain some insight from that study. The other part we want to look at is potential performance benefits from higher number of interleaved tiers. So for instance, right now we consider just a 2-tier structure. Potential benefits with going and having an interleaved multi-tier structure could be now, instead of just block level pipelining, we could implement die level pipelining. So basically getting an increase in overall throughput due to a more pipelined 3D structure. But of course there will be there will be trade-offs in the overall reliability performance. And potentially even the performance metrics from just a raw junction temperature perspective, like how much does it get worse compared to the 2-die structure. And another thing we want to look at is the potential mitigation of resistance drift through a more reliability or a temperature aware partitioning of logic and memory. Consider such like some more interesting approaches than just conventional face-to-face or face-to-back integration. And also we expect to we're working on releasing the integrated framework as an open source tool for the community, and we hope to be able to do that soon in our future publication. So to summarize, we talked about a device system and application level evaluation methodology to quantify impact of different kinds of integration design parameters and architectures on emerging device reliability for compute and memory applications. So we looked at two CIM accelerated designs. We looked at TSV based 3D and monolithic 3D integration. And we evaluated the impact of integration and cooling architectures on the inference accuracy, or the key figure of merit for compute and memory inference, and demonstrated the benefits of potential benefits of advanced cooling. So with that, I'd like to acknowledge the sponsors, SRC as the sponsor of this work, and I'll be happy to take any questions.
Okay, thanks, Anjit, for your very nice presentation. And yeah, so if anyone have question, please unmute yourself or put it in the chat.
Oh, I'm sorry, I just realized my video was off all this while. Apologies.
Okay, I thought that your video is have some problem. Okay, it's fine.
Sorry, I just realized.
So I don't see any questions. So probably I can ask one question is about the thermal issues you mentioned about the monolithic integration. So in your view, I mean, how to in future to solve the thermal coupling between the logic and the memory thermal coupling in the monolithic integration?
Yeah, that's a very good question. I believe I believe just from so there are two key areas we can look at, right? First, of course, is a more design time or early analysis and potential methods of like better architectural um, like partitioning. So for instance, we could do, as Dr. Swaminathan talked today, there's potential for not just die level partitioning, but also block level, IP level, and even transistor level. So as in the case of 3D chiplet or 3D vcache, there was a key reason why the cache was stacked on top of the cache area. But of course, this gets more challenging with monolithic 3D integration, where yeah, you can always do partitioning at any level, but your devices are still much closer. One approach is just partitioning, more thermal aware partitioning, and the other approach that the community is looking at is also development of advanced heat spreaders in the back end, or like closer to the active tier. So for instance, there's research ongoing in aluminum nitride as a potential improved better spreader, which can eliminate the thermal interface material layer and just integrate like your heat spreader just directly to the backside or closer to the device. So essentially, methods of reducing the thermal resistance of the stack, as even Srijit alluded to. But these are a couple of areas I can think of.
Okay, they're very nice. Yeah, very nice. Thank you. Thanks.
Sure.
And yeah, we still have like 2 minutes. And yeah, anyone have a question? Please unmute yourself. Okay. So if not, maybe we can just have a short break and
Sure.
come in 2 minutes. Okay. Thanks.
Sure.
Thanks, Anjit, for great presentation. Yeah.
Thank you, and thank you
Yeah.
for the chance to present.